Last class, there was some really good debate about solutions and domain restrictions when it comes to logarithmic functions. So I wanted to do a little summary of the two schools of thought and then look at what happens graphically. So one argument was that we need to base it off of the most restrictive domain from the original function. If you remember correctly, last class we looked at log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. After we used the properties of logarithms and simplified, we ended up with log base 5 of x squared plus 8x plus 12. When we solved, we either got an answer of -7 or -1. One school of thought was that we needed to base our domain restrictions off of the combined function, versus the other school of thought was we needed to base it off of the original function. Well, let's take a quick look. If I were to look at my original function, if I were to select here and y equals 1, as you can clearly see, there is a point of intersection right here at -1, 1, which definitely corresponds to our idea that we should have a solution when x is -1. However, we also got a second solution at -7. So let's go ahead and turn this one off and let's look at this graph. Here, at log base 5 of x squared plus 8x plus 12, we clearly have two solutions. Now, why did this happen? And look, it does correspond to that -7, 1. Let's think about why this happened. All of a sudden, when we combine this, we are now making everything positive on the inside. Notice my graph changed. This is the graph of the combined versus my original graph. My original graph is the correct graph. When we actually look at the domain of the combined function, we are often going to end up with extraneous solutions. Therefore, when we're looking at logarithmic functions, we need to base our domain restrictions off of our original function. So in this instance, our two domain restrictions, well, here we've got x plus 6, so x has to be greater than -6. Here we've got x plus 2, so x has to be greater than -2. X greater than -6 is the most restrictive domain, so our answers must be greater than -6. So only -1 is a correct solution. Let's look at a second example really quickly. If I were to look at this example, oops, sorry, too much stuff there. If I were to look at this, I've got natural log of x plus natural log of x minus 4 equals natural log of x plus 6. Looking at this, if we're looking at the most restrictive domain for this first equation, so natural log of x, we know x has to be greater than 0. For the second one, x minus 4, x has to be greater than 4. The last one, x has to be greater than -6. So based on this, the most restrictive domain is that x has to be greater than 4. Therefore, our solutions must be greater than 4. If we go through and we solve, first thing we do, addition becomes multiplication, we can combine. Now from here, since we've got a natural log, we've got the same base, we can resimplify. So we've got x times x minus 4 equals x plus 6. Because they're the same base, we know that their arguments are going to be the same. We go through, we follow the algebraic process, we distribute, we get a quadratic, we factor and solve. Here we clearly have two possible options, x equals 6 or x equals -1. But based on our most restrictive domain, the only possible answer is x equals 6. If we were to graph both of these original functions, on the left here and on the right, and see their point of intersection, we're going to see that they only actually have one point of intersection, which corresponds with this x being equal to 6. So let me go over here and let's graph these real quick. I'll turn off these two, and we'll graph here and here. And if I scroll over, you can see I do have only one point of intersection, and it is at 6. So therefore, when you're looking at the domain for a logarithmic function, you need to look at the most restrictive from your original equation. This is similar to when we looked at rational functions and we were talking about domain restrictions. If we looked at it after we had factored out, say we had a whole, and we'd canceled that out, then all of a sudden we didn't see the whole if we looked at the simplified version, so we needed to look at the original function. The same is true with logarithms. I hope this helps clarify.